Now today we are on the topic shear force and bending moment diagram. Shear force and bending moment diagram. In this class we try to understand what is shear force and what is bending moment and what is shear force diagram and bending moment diagram. Now shear force now what is shear force? SF. What is shear force? Shear force is nothing but the algebraic sum of the vertical force at any section of a beam to the right or left of the section is known as shear force. The algebraic sum of the vertical force at any section of a beam to the right or left of the section is known as shear force. And what is bending moment? Bending moment bending moment is nothing but the algebraic sum of the moment of all force acting to the right or left of the section is known as bending moment. Similar definition here, the algebraic sum of the vertical force at any section of the beam to the right or left of the section is known as shear force. Similarly, bending moment is nothing but the algebraic sum of the moment moments of all force acting to the right or left of the section is known as bending moment. Now what is shear force diagram? Here the shear force definition of the shear force, the algebraic sum of the vertical force. Here the bending moment, the definition of the bending moment, the algebraic sum of the moments of all force acting to the right or left of the section is known as bending moment. Here the algebraic sum of the vertical force at any section of a beam to the right or left of the section is known as shear force. Now what is shear force diagram? SFD shear force diagram. Shear force diagram is nothing but one which shows the variation of the shear force along the length of the beam. All the force shows along the length of the beam, all vertical force. A shear force, a shear force diagram is one which shows the variation of the shear force along the length of the beam. And bending moment, and what is the bending moment diagram? Similarly, a bending moment diagram is one which shows the variation of the bending moment along the length of the beam. Obviously, a bending moment diagram is one which shows the variation of the bending moment along the length of the beam. Obviously, we try to draw the bending moment and shear force diagram for beam. Now let me know what are the types of beam. There are so many types of beam. Types of beam. Types of beam. First one is cantilever beam. We try to draw the bending moment and shear force and bending moment diagram of cantilever beam. Cantilever beam. Try to draw the bending moment of simply supported beam. Simply supported beam. SSB, simply supported beam. We try to draw the bending moment diagram of overhanging beam. Hanging beam. Overhanging beam. The cantilever beam like this, one end is fixed and other end is free. This is the cantilever beam. And simply supported beam is like the beam is freely resting on the support, freely resting on the support. And overhanging beam is, the beam is two part, one is simply supported and other portion is like cantilever. This is also freely resting on the support, two support, and one is one side is cantilever. And also overhanging beam can be both side. This is the both side overhanging beam. This is one side, and this is the both side overhang beam, both side. Now try to draw the bending moment and shear force diagram of those beam. Let me first know the sign convention of the shear force and bending moment diagram. What is the sign convention of shear force diagram and sign convention of bending moment diagram? First, try to understand the sign convention of shear force. Sign convention of shear force. Sign convention of shear force. Let me draw a beam, simple beam. Let me draw a simply supported beam. Is freely resting on the support, and at the midpoint I have applied a force, say 1000 Newton. The support reaction will be, let me, this is point A and this is point B and the center point is C. The reaction RA and RB will be 500 Newton and 500 Newton according to Newton's third law. You can also, or taking a at point, any point, moment about any point, you can also consider, because I have directly divided 500 and 500 because the point load acting at the center of the beam. Now let me consider the section. I have cut a section here, say XX section. Now it's divided into two parts. This is the left portion of the beam, left side. The reaction is force is 500 RA, which is RA is equals to 500 Newton. This is the left side section, and this is the right side section of the beam. Is, sorry, this is reaction B. RB is equals to 500 Newton, and the point load at center is 1000 Newton at C, at point C. Now what is the resultant force at right side section, and what is the resultant force at the left side? Obviously at the left side section, the resultant force at left side section is upward direction. 500 Newton is upward direction. And in case of right, this is the left side section, and this is the right side section, and at right side section the resultant force R is equals to what? Our left side, our right side section. Our left side section will be 1000 Newton is downward direction and 500 Newton is upward direction. That means 1000 minus 500 is equals to 500 Newton, which is upward direction. Now we can easily say this is the left side section is upward direction, and also right side section is upward direction. Sorry, this is the downward direction. I am really sorry. This is the downward direction. In case of left side section, the upward direction force, that means the positive shear force, and the left side section is, this is downward, that is a negative shear force. Now we can write down, you can also write down in your copy, write down the shear force at a section will be considered positive. The shear force at a section will be considered positive when the resultant of the force to the left to the section is upward, or to the right of the section is downward. Let me write down. You can easily write down, copy from this note. The shear force, the very important, the sign convention of shear force and bending moment. The shear force at a section will be considered positive when the resultant of the force to the left of the section left of the section is downward. Left of the section is downward. Sorry, left of the section is upward. I am really sorry. Left of the section is upward. Left of the section is upwards, or to the right of the section is downward. The shear force at a section will be considered positive when the resultant of the force to the right, so to the left of the section is upward, or to the right of the section is downward. Similarly, the shear force at a section will be considered negative if the resultant of the force to the left of the section is downward, or to the right of the section is upward. You can easily understand by the diagram. The left side portion is upward, that means positive shear force, and right side portion is downward, that means resultant force is downward, that means positive shear force. If the right side portion, the resultant force is upward, then the shear force will be negative. Here I have write the shear force at a section will be considered positive when the resultant force to the left of the section is downward, or to the right of the section, left of the section is upward, or to the right of the section is downward. Left section is upward, and right section is downward resultant force. In case of left side is downward, that means negative shear force. In case of negative shear force, resultant force will be downward at left side section and resultant force will be upward at the right side section. Now try to understand the bending sign convention of bending moment diagram. Sign convention of bending moment diagram. I think you have clearly the sign convention of shear. What will be the sign convention of shear force diagram of a beam by subjected to by acting a load on the beam in respect of support reaction and applied load, that is the external load, and these are the internal reaction RA and RB. Now try to understand the bending moment, the sign convention of a bending moment diagram. Sign convention for bending moment. For bending moment, in case of bending moment, the negative bending moment, that means the curvature of the beam, like convexity, top fiber, only top fiber and convexity, the shape of the convexity, this is the convex type, this curve like convexity, and this is the concavity. That means the bending moment diagram will be negative. The bending moment diagram will be negative. If the shape of the curvature like concavity, top fiber is concavity. This is a concavity. This top fiber is concavity. Concavity, and this is convexity. The bending moment will be, in this case, bending moment will be positive bending moment. Positive bending moment. In this case, bending moment will be negative bending moment. Now you can write down the sign convention for bending moment. The bending moment, I write now, the bending moment at a section is considered positive if the bending moment at that section is such that it tends to bend the beam to a curvature having concavity at the top. at the top. At the top, the bending moment, consider bending moment, positive bending moment. Consider positive bending moment if the bending moment at the section is such that tends to bend the beam to a curvature having concavity. Look at the concavity curvature. This is the concavity. Top top fiber is concavity. That means this is, in this case the bending moment will be positive. Similarly, 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 the bending moment at a section is considered negative if the bending moment at that section is such that it tends to bend the beam to a curvature having convexity. At the top, and concavity at the bottom, that means in this case the bending moment is negative. The top fiber is convexity and bottom fiber is concavity. The curvature of the beam like this, and in case of positive bending moment the curvature will be like this. Now the bending or the positive bending moment may be called, it can be called it can be called sagging moment, and the negative bending moment called hogging moment. Let me write. The positive bending moment is called sagging moment, and negative bending moment is called hogging moment. Negative bending moment is called hogging moment. Now try to draw the bending moment and shear force diagram of a cantilever beam subjected to a point load at free end. Now try to draw the cantilever beam is subjected to a point load at free end. This point load free end is say W. W is in Newton or kilonewton. This is the weight or the force unit of the force, and the length of the beam, let me the length of the beam say L. This is the point A and this is the point B. Now shear force at that point, at point B, is total load at that point. What is the total load at point? Total load at that point is W. The shear force at point B is shear force at find out the shear force, then draw the shear force diagram. Shear force at point B, say FB. Shear force at point B, say FB, is downward direction. That means positive shear force plus W. In the beam, shear force also be positive at point A. The shear force at point A is also positive shear force W. The shear force diagram of that cantilever beam, of this cantilever beam, this is the base, this is a shear force is constant value, the straight line, this is the shear force diagram positive, this is a positive shear force diagram. This is a shear force diagram, SFD. In case of bending moment, the beam tends like bend like this. That means top fiber is what? Top fiber is convexity. Convexity means negative bending moment. The bending moment will be negative for cantilever beam. This is the top fiber is convexity. That means a negative bending moment. Here also, if I apply load at the point at free end, the beam will bend like this, means like convexity, sorry, yes, convexity. So the bending moment at point B, what? Bending moment at point B, M at point B. What is the moment? Moment is equals to, moment is defined as the force into perpendicular distance, perpendicular CG distance. At that point, load, apply the load W and perpendicular distance is 0. That means moment at point B is equals to 0. Obviously, in cantilever beam at free end, bending moment always 0, and the bending moment at point A, bending moment at point A is equals to minus, that is negative bending moment, that because of the bend the beam bend like convexity, that means the negative bending moment. So the bending moment will be W into perpendicular distance is L, W into L. This is the linear equation. Linear equation. This is the linear equation. So it will be linear, that means linear curve. The now the shape of the bending moment diagram will be like this is the base of the, this is a beam, base of the beam, this is a base, and bending moment at point B is equals to 0, and bending moment at point A is equals to minus WL. So down in from below the base, I am draw the upper side. There I have no space in lower side. Let me draw the upper side. You can imagine it. This is the W into L. This is the linear shape. Linear shape. This is a negative bending moment. Negative bending moment. I put the sign negative. There's no problem. There is no problem at all. The bending moment is W into L. W into L. This is the bending moment diagram. Now try to draw the bending moment diagram of same beam in difference point load, in multiple point load. Let me draw the cantilever beam. Cantilever beam subjected to multiple point load. This is load, say I have chosen value 10 kilonewton. Here point load is say 20 kilonewton, and here also point load say 30 kilonewton. Now try to draw the bending moment and shear force diagram of that beam. Now find out the shear force. Shear force. Then we will easily draw the shear force diagram. of that beam. Say this is point A and this is point B. In between B and A and B, like I have choose the point, this is the point C and this is point D. At point B, the shear force is total load at point B is 10 kilonewton. The shear force at point B is equals to plus 10 kilonewton downward. And shear force at point D, just right to D and just left to D. Shear force at point D, just left, just right, just right will be 10, just right will be load at point B, that is plus 10 kilonewton, and just left to the D will be load at point B plus load on the point D, that means 20. That means shear force at point D is 30 kilonewton. And shear force at point C, now the find out the shear force at point C. Here also shear force at point C, just right and just left. Shear force at point C just to right is equals to shear force at point D just to left is equals to shear force at point D just to left. What is the value? 30 kilonewton. And shear force at point C just left will be shear force at point just left, shear force at point just right, that is 30 kilonewton, 30 plus load at point C. Load at point C is equal to 30, that means 60 kilonewton. Now shear force at point A. Shear force at point A is equals to, there is no load at point A, that means the shear force will be at point C left, that means 60 kilonewton. Now draw the shear force diagram for the cantilever beam. Here I have try to draw the shear force diagram. All the value are shown here. I can easily draw the shear force diagram here by using all the values. The shear force at point B is equals to 10 kilonewton. This is the B point B, and this is point D, and this is point C, and this is point A. The shear force at point B is positive 10 kilonewton, that means upward direction, say this is the 10 kilonewton. Now shear force at point D, just right side, is also 10 kilonewton. This is the 10 kilonewton, just to right, and just to left is what? Just to left is 30 kilonewton. Just to left is 30 kilonewton. Here this 30 kilonewton also. At that point, at point B, at point D, there is two value of the shear force, that is 30 kilonewton and 20 kilonewton. And point C, the shear force is just to right is also 30 kilonewton. This is a 30 kilonewton point, and just to left is 60 kilonewton. And point A is shear force is 60 kilonewton. Finish. This is a positive shear force. Now find out the value of bending moment of that beam. Bending moment. Bending moment at point, always at free end the bending moment is 0. I can write easily the bending moment at point B is equals to 0. This beam will be bend like convexity. That means negative bending moment. All that point the bending moment will be negative. Now the bending moment at point D is equals to minus, what will be the bending moment at point B? Force at point D into perpendicular distance up to D. Let me the perpendicular distance, choose the length of the beam. Let me, I miss out the length of the beam. Let me the length of the beam is, this is 2 meter, this is 1.5 meter, and this is like, you can say, you can consider 1 meter. Now perpendicular distance is 1 meter up to D from B is equals to bending moment at point D will be 10 into perpendicular distance 1. That means 10 kilonewton meter. Force into perpendicular distance, force is Newton and perpendicular distance is meter, 1 meter. That means kilonewton into meter, kilonewton meter. Or you can write also or kilonewton meter. Now find out the bending moment at point C. What will be the bending moment at point C? At point C, the bending moment will be minus, negative. Point at load at point B into perpendicular distance up to C, load at plus load at point D into perpendicular distance from D to C. That means load at point B is equals to 10 into perpendicular distance 1 meter plus 1 meter plus 1.5 meter, 1 plus 1.5 meter perpendicular distance, and plus for the load at point D, the bending moment at point C will be load at point D into perpendicular distance from D to C. That means 20 kilonewton at point D, load at point D into perpendicular distance is 1.5. Now the total value of the bending moment at point C, this value is minus 2.5 into 10, that means 25, plus 20 into 1.5, that means 30. Yes, 30. That means minus 55 kilonewton meter. Now find out the bending moment at point A. We have find out the bending moment at point B, that is 0. We also find out the bending moment. Find it at point D, bending moment is minus 10 kilonewton meters, and the bending moment at point C we have find out minus 55 kilonewton meter. Now find out the bending moment at point A, that is minus point load at point B into perpendicular distance from B to A, that is 1 meter plus 1.5 meter plus 2 meter, that means 3.5 plus 1 is, that means 4 meter. 10 into 4.5 meter. Point load at point B, 10 into perpendicular distance, that is 1 meter plus 1.5 plus 2 meter. And for 20 kilonewton load at point D, 20 into 1.5 plus 2. For the load at point C, 30 kilonewton plus 30 into perpendicular distance is 2 meter. That means the total value will be resistive 4.5 into 10 is equals to minus 4.5 into 10 45 plus 3.5 into 20, that means 3 into 20 60 plus 10 70, 70 plus 30 into 2, that means 60. Total value 105 175 minus 175 kilonewton meter. Now try to draw the bending moment diagram. I have to draw the bending moment diagram here. The base bending moment at point B is equals to 0, not need to draw. This is a point B, bending moment equals to 0, moment at point B is equals to 0. Bending moment at point D is equals to minus 10 kilonewton meter. Let me the 10 kilonewton meter is here. This is a linear form. This all are the value, all the equation are linear equation, like y equals to mx plus c. In this form, all are the linear equation. Bending moment at point C is equals to minus 55. Say consider the minus 55 point C is here. This is the point C, minus 55, and bending moment at point A is equals to minus 175. This is the 175. The bending moment at point A is minus 175. Bending moment at point A is equals to minus 175. Bending moment at point C is equals to minus 55. Bending moment at point D is equals to minus 10 kilonewton. 10 minus 10. Now draw the diagram. This linear curve, the bending moment is, this is the bending moment diagram of cantilever beam subject to different point load and at different point. This is a negative bending, totally negative bending moment. I hope you understand the bending moment diagram of a cantilever beam and shear force diagram, how to draw the shear force diagram of a cantilever beam, and also bending moment diagram. This is the bending moment diagram. In next class, I try to draw the bending moment diagram of cantilever beam subjected to uniform distributed load. Uniform distributed load in the next class. This is the uniform distributed load. Uniform distributed load. In the next class, I try to draw the bending moment and shear force diagram for that beam. Thank you so much.